Okay, what do we got here? That is the question. We're going to start by opening it up. It was given to me recently, and the quick thing that everybody thinks of, since it's 480, we think it's three-phase. Some of the breakers in it were 240, and as I looked at them a little bit, they appear to be two-pole. And two-pole is not normally used for three-phase. Now, I say not normally, we'll go back to the whiteboard and show how you could use a two-pole on 480, and a friend of mine did that years ago, and it worked for their installation, saving considerable money on each of the breakers. You're not going to get by with a single pole. That's going to be illegal. But one of the things you'd have to do, like where this says 100 amp, 100 phase 1, you would have to, phase 1, 3 wire, I think. I think that's 3. Anyway, you would have to relabel it. Because if you were using this for 483 phase, you need to relabel it so that people know what's what. Okay, what we have here, we have, it came in, it was bottom feeder. That's interesting. Actually, there's no knockouts. It's actually new. I know it looked fairly good. I hadn't really realized that. Yeah, this is meant to be a bottom feeder, but there's no holes. It's actually a new box. So it was a good gift anyway. So we have two lines coming in. They're running up here. What do we have? We have got this one here. It says it's a 240 volt breaker. It connects to one pole over there. That is a 240. It's a two-pole breaker, but it's only connected on one pole. Or am I just seeing it wrong? That probably travels back there. No, it's connected on both. It's just the blank space was confusing me. It's connected on both. And 240, 240, 480. 480 has more insulation. This does not quite make sense to me. Why would we have the 480s with more insulation? Let's get a better view of what's going on underneath here. I think it's just two bus bars running all the way down. But why? And on a new panel too. Obviously we could not use the 240 volt breakers for 480. The fact that this says it's 240 and 480, we could have, oops, what's that one? Okay, screwdriver. No, that's not it. That's terminal lug. I didn't bring a screwdriver for that one. This would be a neutral. Nobody hooks up to the neutral, of course. I could see it if we had one bus bar that's 240, one that's 480, and a neutral that's below that. I could see that, but I'm not quite seeing the connections because, okay, if we're coming across the two, we'd still have 240 across the two. Does that? Okay, that goes underneath there without, that is. Okay, no. This is a 480 terminal. That's 480 in. This is 240 in. And these are 480 single phase, and they're getting that from the neutral and the 480 terminal. That one's still going, we're still going across there. Nah, that still don't make sense. I don't know how they got away with that legally. I don't know. I don't get it. Okay. Just for curiosity, it's going to be, all kinds of people are going to say, I wish you would have opened it up more. Now we're all curious. Let's open up some of these breakers, especially being a new panel. I'm going to grab another screwdriver so we can pull that off. Take a look and have a see what it is. Then we'll go in and talk about using the two-pole 480 breakers for three-phase. What you end up doing, and some of you already know, is you do a corner grounded 480 delta, which you actually, as long as the center was not hooked up, it could be a isolated Y also. It doesn't really matter, but you definitely don't want a grounded Y. So just to end the curiosity here. Yeah, the little terminal screws are a problem. I'm just kind of letting them fall in the box for the most part, down here in the bottom. I've got some of these similar breakers in three-phase, but the bus bars are not set up for it. It's still a panel that holds them. And it could be set up. I could put in a third bus and a little bit of metal. I don't really like the corner grounded 483 phase, like I will explain, but it is an option. Okay, so we have two 480 breakers right here. Both of them connected to the two hot lines, and a 240 breaker up here, both connected to the same hot lines. So, yeah.
That doesn't seem kosher.
No. Maybe there's a reason why this was new military surplus, or somebody surplus. It looks military-ish. And it came from similar type. It's been passed around in a few shops previous to this. Definitely 480 breakers, definitely 240. I've also seen people use 240 on 480 when nobody was checking for inspecting or anything. So a lot of times they're the same thing. They're not always, but a lot of times they are the same thing, just with different rating classes. And you pay more for the higher rating class. So, well, I wouldn't guarantee that they're the same, because you should have a little bit stronger trip spring in a 480. It should break quicker. There's some things that should be different, but some of the manufacturers basically make a 600 volt breaker, and then why make a second one even though you could make it cheaper?
Yeah, I did notice the 480 breaker. It's labeled 480, but it has ratings for 480 and 240 on the back.
Yeah, that's fine. That's all fine. It's just the other ones here are 240 with no other choices. I mean, it's just strictly a 240. And the panel says it's a 240/480, which I can see it being a 240/480, where you would have, on the other hand, your two neutral voltage is really only 240 on those, but you got 480 between the two terminals. So I don't know. It might be legal to use either style in this, the way it appears, because while you have 480 volts across these two, your real grounding normally goes to neutral, and you're only 240 to neutral from one leg, 240 from the other, and 480 between the two of them. So I don't know. I don't know. It's interesting. Let's move into the office. I'll let Bert screw that back together so it's not such a mess later. It's nice to have employees. Oops. Yeah, just leave them out. Okay. Okay. And here is not W, N. There's neutral. Okay. This is what it looks like we've got in that box, and this one over here would be 240 above the neutral. This one would also be 240, and then in between the two, I play with all my colors today, just because I can. In between the two, of course, we would have 480. Now, pretty much all of your power is actually generated on a three-phase system. So we'd have another set there, another here. And so up here, if we had more connections, that other connection, which is not in the box, we would have from there to there, we would have 480. And we'd have 480 over here, if that was connected up with the three-phase. But it would be most likely, if you were using that, you'd connect on another leg over here, which would be center tapped again for another box of single phase, another box of single phase. So what the other concept that I was talking about that you can do, because the thing is, with that one, I guess I should have left it up, but if you turn the breaker off that goes to your two 240s, you're dead. There's no power there. You're just connected to neutral only. Well, we can do the same thing. Let's say that we have a delta. Each of these are 480 volt. 480 and 480. And then we take one leg over here, and I don't like, I drew it just like most people do in the books, and I don't actually like that. It's the same idea, but it's not as clear to the world, because you normally do draw deltas in that direction, but let's just draw it this way. Let's go up that way. We'll make it a little bigger. Go up that way, and then go across them. So now we have 480, 480, and 480. And you take this one here and you ground it and make it your neutral. So now you have a breaker off of this point and a breaker off of this point. And you end up with, from those two terminals, you've got 480 to ground on both of them, and then you have your neutral. Those two will shut the power off, and your neutral can still be connected. Now, the thing about this is that your voltage above neutral is 480 volts, where what we have most of the time in North America is we have a Y connected, which has a 277, and your ground comes off in the middle right here, and this is a 277, and this is a 277 volt, and your voltage in between these two, as the 277s add up and they're at a little bit of an offset phase, is 480. So you've got, this is your more common way you have is you have a 480/277. Now on this one here, you have just straight 480. So anything you want to run is going to have to come off of a transformer. You put transformer across, I would choose to put it across the two hot legs up here as opposed to onto a neutral. While you could do one on a neutral, but I'd rather myself have it on the two upper legs for a transformer that goes from 480 to your control voltage. So when you shut off your breakers, everything's dead, including your transformer without a question. Now granted, this, you can have one leg of it and you're neutral, this is going to kill it. You're still killing that transformer. I just prefer to have it on the double brake side. That's personal preference, not legally needed. But it allows you to use two pole breakers by doing this. And the way you will normally see it, they call it corner grounded or a corner neutral, which is fine. But the way that they normally write it is like I was starting to do earlier. And they do it like this, and then they show the ground coming off on one corner with the line straight across. To me, that's a little bit, didn't seem as nice because we have 480 volts that we're showing going one direction and then 480 up and 480 up. This one here, I like the fact that it's nothing there. It's 480 up, and 480 across. But that's just personal preference of presenting it. And what is three-phase versus single-phase? What is it? I mean, what's the real difference? We just got these voltages between parts. But what we've got, essentially, we would have, this is very basic, but we would have a set of windings and a set of windings and a set of windings. And in the middle of this, a north and south rotating magnet. And if this rotates around in here, you can see in one, as the North Pole comes by, it pushes electricity. South Pole comes by, it pulls it that way as this rotates around. So if we look at just one coil, one set here, it's single phase. And what happens is we just follow the north. It pushes electricity to that point. Then it's coming down here and it's pushing it here. It's pushing it here. Instead of having just strictly your electricity going back and forth, you have a continuous rotation of the push of your electricity. So while each one of these sets is going back and forth, there is a continuous wave that is pushed around in a circle. And that gives you your self-starting that you have with three-phase. You can do a single phase, and you can have one coil. Once it starts running so it's close to speed, another coil on a motor will keep it going. So that's where a single-phase motor has some way of getting it moving to start with. And you do the same thing with a three-phase rotary phase converter. And we'll talk, and part of this is I just decided to break into this right now. We will do some talking about rotary phase converters. We will do some little tests and things that I did before I built my first one. I've built quite a few of them now. First one I built for myself after, in fact, watching some, was I watching YouTube at that time or just seeing people? I saw part of it was a video, but the guy didn't explain it very well. I don't know if it was on YouTube or not. It was, I've had three-phase for 24 years. I don't know how long YouTube's been out there doing stuff. I may have just imagined it. It might have been an embedded video in some instructional separate site too. I kind of am thinking it was, there was a bit of a video I saw, but it didn't have that much. And yeah, this would have been back 1998-ish that I was looking at it. I know I saw something on the internet. Anyway, the big thing is that you get that field that rolls around. Now, another thing they used to do early on, they had similar concept, but not quite. They had the idea of a two-phase. And so you had a coil here, and then they figured they'd put one at 90 degrees electrically, And that also will give you this pulling. But when they ran these, they had 2 wires for this one, 2 wires for this one. So you had 4 wires, and you really didn't have as efficient of a continuity here as you did with the 3. And as simple as it is, it just was a later idea. They did the first ones with a matter of 2 generators. And I think where that comes from is the same as the putting your cylinders on your steam locomotive at 90 degrees apart from each other. And so I think that was just an automatic thing once they realized they could do a brushless AC motor, but it wasn't self-starting. If you did 2 of them and put them, then they could be self-starting the same way that a locomotive is. But the 3-phase, just playing with 3 wires, and they do a conversion with some voltage changes, and it's not quite right, but where they'll take the 4-wire, 2-phase old systems on the East Coast. I don't know if there are any yet or not. There were still 30 years ago when I was looking at this. And they'll do a conversion and pull it into a regular 3-phase. And you're not quite as efficient, but the 2 will interchange with a little bit of transformer voltage differences on the end. So the big thing where people that work with 3-phase all the time, you learn a lot of things, and you can have 3-phase that is actually, you can have 110 or 120 volt 3-phase even. You don't see that very often. And there might be some reasons for that for some people where you've only got 110 volts to work with. And you can feed an inverter with 110 volts that was meant, some of them are meant to go 110 input and they put 220 output. But those are limited in their size. So you might have a situation where you want to do 110 volt input, put it into an oversized 240 volt inverter, and then make and still running with 110, which it could not have over the 110 output normally. So you would run that and run a 120 volt 3-phase motor, which is a matter of taking a standard 240 volt 3-phase motor, breaking the windings and rewiring them. It's not something that you're going to, breaking them out, not breaking them, because if you just ruin it, you ruined it. But the bigger thing I was wanting to do right away is just, let's say, because this is a big thing, you're looking for a shop. And let's say that you know, let's say that you know that you're going to run an industrial shop. And I've seen a lot of people do this. Before they really get into it, they hadn't planned. And one of my things I did when I was first looking for a shop, every time I'd see a shop, I look up overhead. See these lines on this side? That's single phase. This is single phase over here. In fact, this is a real basic single phase with 1 neutral and 1 wire. See the 3 insulated lines over on the other side up on the pole? That's 3-phase over there. So when I bought this shop, I saw the 3-phase that was actually 2 poles away at that time, and believed that I had 3-phase here in part because the shop was also wired with 3-phase. I failed on that one. I at least had looked to see it was close enough, but I didn't actually check with the utility company. So it's better yet if you even check with this utility company. While we can do these things to make stuff run on single phase, if you're stuck with that, if you're looking at buying a shop and you know that you're going to run industrial stuff, another guy here that I know fairly nearby, he spent $800,000 building a shop in this area. It's $200,000 for him to get 3-phase power where he's at. He's not getting 3-phase power, so he deals with single-phase power. He fires up a generator when he wants to run 3-phase. Lots of people I've seen do this mistake. It's not the end of the world, and it might not be a reason to move, but when you're first looking around and thinking of a place for a shop, keep it in mind. Keep it in mind. And if the three-phase is not there, your first indicator is looking at the poles, but you still need to talk to the utility. Now, what I found out when I finally went and talked to the utility, supposedly there was, when I bought the shop, they were saying it was like $17,000 to hook up to power. And I come to find out when I actually talked to the utility company that it didn't cost $17,000. The rumor was, because I was dealing on rumor mill since I'd been around the shop and other people had before me, the rumor mill was that they had left a big bill here from all the electricity that they were using when the shop was used before, and you had to pay that. Well, I went to the utility. Utility had no record of any power being at this shop before I hooked up to it. None. So at least that was good. I hooked up the single phase here first. I hooked up the single phase. I spent my $15 filing fee, put in my meter, which I actually put on the neighbor's property because I also didn't check my property lines very well. Ran the wire over. I thought that was the old meter that everybody had just forgot about. No, it was 5 foot on my neighbor's property from an old burnt down cabin. And I pulled that junky pole out, put in a new pole, but I put it on the neighbor's. I even moved where it is now is 5 foot on his property. I moved like 10 foot closer to my side to make sure I was on in case there was a mistake. Well, I didn't quite make it. The neighbor is nice. Didn't have to move the pole once I found that out. It's okay. He's allowing me to keep using it. So that's the single phase that comes into my shop. I initially used the single phase for a long time. I talked to the utility, and they told me that the three-phase was down there 2 poles, and that was the point where it really clicked and I understood, okay, during the pipeline, when this shop was first built in 1971, what is now my tool room and white room, we call it, was a generator shack. And it had, when I first saw the shop, it had a little baby lister in there. Well, it had some kind of a bigger international harvester diesel generator in there before the guys moved in the shop that were here. That originally powered this plus a 20-man man camp that was further back on the property. I've dug up some of the other wires and things over time. So, and there was utility water lines that flowed around between the multiple buildings. There was quite a bit more here than when I got the shop, but it had never been connected to the utility. So my idea of this three-phase that would be available, because it kind of looked like it, and no, it was 2 power poles away. So the end of it was, we kind of went back and forth, and one day they gave me a lower price for hooking up to three-phase than they had before. And so that plus my boxes, I had about 20 grand in it, and I had three-phase, so I'm good. And it was well worth buying, well worth putting in. That's nothing. Another friend of mine, in his shop, we put in his three-phase for $15. Same thing as when I put in my single-phase. He was in the right place. And he hadn't planned on needing three-phase, but he decided he wanted it when he put in a big 4-sided planer for planing log cabin siding. And anyway, so I first put in the rotary phase converter. I probably used it for, well, even after I got the three-phase, I used it for quite a while. There was 2 years where I had the three-phase, but I hadn't spent any extra money to distribute it out. It ran 1 drill press up at the front of the shop. That first little drill, that's all it did for a couple years while I was still running on the rotary phase converter I built at the back of the shop. Then when I got the job to work on the locomotive, I said, oh, got to clear everything out. Let's put some wiring in. Let's do this. And I kind of shotgunned it and spent a bunch of money on it and got the three-phase going down 1 wall. And so anyway, yeah, it's good to look, pay attention, because if you can get three-phase, it's so nice. The big thing you can do, if you've only got a few machines, you can put inverters on them. It works. It's not terrible. If you have quite a few machines, you can do a rotary phase converter. The real thing that bothers you about that, though, is either going over to turn on the phase converter, which I usually try and set them up anymore so they have switches at the machines. But if there's more than one person in the shop, somebody else has turned it on when you don't want it on because they've got to use it for their machine. And the problem with that is it's just an aggravation. You hear this extra motor running when things could be quieter. And you lose a little bit of efficiency. It works. And it is a way to get by. Yeah, it's a way to get by. It lets you do things. But if you're doing, and if you're doing a lot of it too, even if you're doing a rotary phase converter, you want to do your phase converter, you come into a panel, and then you distribute your three-phase out again from there. You don't want to just do a bunch of different phase converters. You want to do one and run it to all your machines. Pretend like you actually had three-phase in the shop, because you do once you convert it with a rotary phase converter. Let's go back. Let's talk a little bit about an inverter, just in general. And then I may visit this some more, or I may just drop off for the time. We will talk about building rotary phase converters, because there's some things, and I do them a little bit different than most of the guys building them. Let's say we have our VFD, and I could draw a bunch of them on here because there's usually multiples, but I'm going to do it the other way. You have a big capacitor. So there, you have a big capacitor. Okay, and you have your power coming in. You have a line and a neutral, and we're going to have a diode in here. Well, I should just plain. I know we're going to draw a full. Well, we'll draw it one at a time, as I started that way. So, okay, we got a diode in here. It's going that way. We have, from this side, we have a diode into here that is also going that way. And then over to the other pole, we have a diode, and it is the other direction. And then from here, we have another diode into here, which is again going that way. And the way you usually see that bridge, which is a little bit cleaner looking, is you'll have it, it's and you will have AC going on one part, and you will have DC going out on the other part. So we'll have this one going out, this one going out, and this is our other DC. So yeah, those two are going that way. These two have to go this way. Right? Yeah. Yeah. So that as you get to AC at one point, this one here being AC, this being AC, and the current flows that way. I believe this should be the plus and this should be the minus. You'll see a lot of these when you buy them in the bridge. They will have just one corner that's marked, and that's marked for the plus only when they come as a diode block. In your inverter, they're normally put in here as, sometimes they're blocks, but on the bigger ones you'll have individual diodes you can see. The thing that happens with this, and then
off of here. I'm just going to simplify the next step here, and this is gate transistors that are computer controlled. And from those transistors, which there will be negative and positive pairs usually, so that they can fire off of the two sides of the DC that you store up in here. Because that's all you're doing, is you're storing in the capacitor the same as if it is a battery. But it's a fast recovery, short-term battery. And so what you end up doing then is your plus and minus from there, here, comes in, and then you have your full three-phase that comes out because it switches. Each of the transistors switches so that it connects quickly to each of these and rotates how the three-phase is made, and I'm not going to get into the whole, it's very basic. But the important thing in working with these, when we're doing things that we're stretching the limits, this capacitor, when you first turn this on, will take a lot of inrush current. And this will damage small generators. It will trip breakers. You only need to run for your 5-horse motor, you might only need a 10 amp breaker on your 240, but you're going to need a 40 amp breaker to turn the thing on. So now there's a way around that works really good. Instead of connecting right to our neutral and line here, first off, we connect, and the one I like, some kind of a resistor, but I like to use a light bulb across there. And the reason I like a light bulb is because you turn on your light bulb and your lights light up bright at first, and they suck up all of the power. They don't let it go into the capacitor. Over time, they will go dim and they will quit using the power. The power will have stored up in the capacitor. It's no longer going through there. Now you have a fully charged capacitor. Now you turn on a switch that you've put in here, and you close the switch, and you close this switch. Once you see those lights go out, the simple way to do this on an AC system is you have two of your breakers. You have the last one I did, we had a 15 amp, and we were running and I think we had a 100 amp. We were running on 241 phase, we were running a 20 horse motor at full 20 horse. And we had the 15 amp that fed into the two lights that were running, charging the capacitors. And then once the lights would go out, then we'd flip on the 100 amp. The 15 amp could stay on, it didn't really matter. But you want to switch them both off when you're killing the whole system. Now, there is another thing with this too, as far as what I did on that one, because they do not make, in the normal course of events, a 20 horsepower, 240 volt single phase input frequency inverter, frequency drive. So what I did was I disconnected the original capacitors that were in here, and I made a whole larger bank of capacitors along with putting in larger diodes to charge them up, and then ran down with cables to go into the inverter that was originally made for three-phase input. Because on the three-phase, it had less capacitor because it gets charged more often off of three-phase. So you don't need as big of a capacitor. Single phase, you need more capacitor. And I went overkill. I tripled the size of the capacitors, which I know is more than I need, but I wanted to make sure that it wasn't a problem. On the other hand of that, though, you have to remember about your peak voltages that come up. And he was a little over on the peak voltage where he was at, and I think I was using 360 volt capacitors at first, and anyway, they exploded. So we went to 600 volt capacitors, and it's good now. He used it for a few years. He hasn't used it for over 10 years now. That piece of equipment is no longer even in the shop. So, and the reason we did that at his shop, he actually had 483 phase. In fact, he had 483 phase. We put in a dry transformer to give him 208. And he had that because you get charged a load demand if you use too much power. So by drawing off of both meters, we were able to run all of the equipment that he was running without getting a load charge. We could pull 49.5 kilowatts off of one meter. We could pull another 20 kilowatts off the other meter. So that worked out because 50 kilowatts is where you're a bad boy and you get charged a whole lot more. But if you have 2 meters, well, you get twice 50 kilowatts. So we were well under our limit. And that's a lot cheaper at $20-some per meter per month versus the load demand charges. Okay, we're talking about, let's just talk about a couple of other things here. Some rambling on with general 3-phase. Let's talk about 208, which you will see regularly. And this is a 120 volt nominal coil, 120, and you have 208 volts across here, 208 across there, 208 across there. This is a normal 3-phase, 3 lines coming in. This one here is grounded and you're neutral. Reason you do that is because you can have easily your 120 for your plug-ins. You have 3 single-phase breakers that you'll put in a row. So you'll have 3. But what you don't have is you don't have 240 volts for running single-phase. You have 208 for running single-phase. So because these do not add directly together. If you come down here and you use this and a neutral, you don't have that 240 there. Now you can add in a bucking transformer and you can boosting transformer and you can boost that up to 240. That is the one downside. One of the plus sides of this, besides the fact of having 3 possibles for your 110 plugs, one of the big pluses is that your ground to neutral is a maximum of 120 volts. So you do not get shocked with anything over 120 volts if you're connecting to one of the conductors somewhere. That's your maximum. So I will do that as wiring a lot of times for mining equipment because besides adding in ground faults, it's just less voltage to have the potential of people getting electrocuted off of. Now, another one, and you will see this in a lot of old buildings, and it's suggested a lot of times it's not a bad thing, but it is different and it is something to be aware of, is you have a 120 and a 120 and a 240 and a 240. And this is a high leg 240. And this is fairly common. Not as common as the 208 for new installations. And the advantage to this is on your single phase, you have single phase breaker, single phase breaker. Do not use this one for single phase. This is 269 volts above the ground. This terminal here will drop you on your butt. On your 3-phase with your 480 with a center Y, we only had 277 to ground. So this is nearly as dangerous as the 277 on the 480. Make sure you mark your high leg. In fact, a friend of mine, they made that mistake and they wired a whole bunch of his lights in from here to here instead of from here. This was fine for his fluorescence. This was fine. He had somebody helping him. They wired on this, put a single breakers in on the wrong place on the breaker panel, and he didn't know. Yeah, it made lots of pretty sparks after it blew out all the bulbs. So this has the advantage, it has a safety disadvantage, but it gives you all of what you're doing, and usually they will put in heavier transformers on this part of it up on the pole than they will on this part, so that you can have more power available for your single phase load, because that's what they're trying to do, is get everything for all that you need for single phase and for three phase. You can also take the 208, and if you want a full 240, you can do a boost transformer on each of them to add to the voltage. And we had another video talking about bucking and boosting and showing that with the bucking transformer I set up for my 380 out here. I'm sure we can link that too. But okay, I'm bored on talking on three-phase right now. We'll get back to it sometime and talk about how to build rotary phase converters, because for you guys that don't have one, you might as well build it. And oh, that's the other thing too. That thing I was talking about with the inrush to the capacitor, using the light bulbs or a resistor. I like light bulbs because you can see them. Incandescent, forget the LED, ain't gonna work. Incandescent, real light bulbs with gas in them, or a vacuum. Anyway, excellent for a generator system. I set up a bunch of equipment for a guy. He's only got a 6 kilowatt diesel generator. He's running a whole bunch of motors that you could never start on that. And there's no way you're going to do it other than with the variable frequency drive and a charging system to get it started. But he's running a bunch of motors, works fine for him, no starting problems. But you would fry everything if you just turned those inverters on without charging the capacitors first. And we went on that one, instead of modifying the inverters, we used bigger inverters than what we needed, so that they had big enough capacitors for the job.